Today, I'm going to deliver a lecture on resource allocation and D2D communication. Later on, first I'll discuss on resource allocation in wireless communication. Thereafter, I'll extend this discussion to device-to-device communication. Let me share my slides. Bhaskar, just check, is it visible? Bhaskar?
Yes, sir. Yes, sir. It's loading, sir.
Just a minute.
Yes, sir. It's visible.
But I can't see it right now. Maybe.
Sir, give hide option, sir.
Huh?
That meetgoogle.com. Yes, sir. Give hide options.
No, that is okay, but it is not visible
No, it is
to
visible,
me.
sir. It is visible.
But I can't see. Just a minute. Is it visible? No.
Yes, sir.
No. Is it okay?
Yes, sir. Put it slideshow, sir.
I'm going to back to slideshow. Okay. Is it fine?
Yes, sir. Visible, sir.
Okay. Just a minute. Just a minute. Just a minute. Now just see. I'm adding my slides. Now it is visible. Is it okay? Slide mode?
Yes, sir. It is visible, sir. Yes, sir.
Okay. Thank you. Today's topic of discussion is resource allocation in wireless networks, optimization and D2D communication perspective. This is my discussion outline, introduction, then optimization approaches, optimization techniques, D2D communication, case study 1, case study 2, conclusion and references. See, what are wireless resources basically? Means when we do the communications between transmitter and receivers, what are the resources are basically used? One is a spectrum, transmit power, time slots, and spatial. So basically, antennas are used for communication, and different multiple access techniques are there also. Okay, first come to the point: spectrum and frequency blocks. Basically, if you want to transmit any data, you have to say transmit the information through a medium. Here it is a spectrum band. That depends on different technology and generations and requirement. That band is different. Say today if you think about a Wi-Fi, it is 2.4G. We think about sub-6 gigahertz band, it is approximately to 1 to 8 gigahertz. Okay. If we think about the GSM bands, it is a 900 megahertz band. Now, the spectrum band and the frequency block, there is a little bit difference. When I'm talking about frequency blocks, that means the total entire band, the total available entire band means basically you can say channel bandwidth is dedicated, not only dedicated for a single transmission, maybe a frequency block transmission. For an example, say if I think about 4G transmission modulation technique, that is OFDM, where each frame contains multiple subcarriers, and each subcarrier contains some bandwidth. So say there are m number of subcarriers and each is carrying k band. So total one resource block you can say m into k. If k K is the total. K is the M is the total bandwidth used for one subcarrier, and K is the number of subcarriers. So one resource block is equal to M in K band. So one channel may carry number of resource blocks. So depends on your application, depends on communication technology, that frequency block, number of frequency blocks varies. If we think from transmit power, when a signal is transmitted from a transmitter to a receiver, the transmitter transmits the information with some power. If it is a single user, no problem. If there are multiple users, then there is a problem. Say, out of say m number of users, if one of them transmit with a high frequency, high power, then its transmission may create an interference to other m minus 1 number of users first. Second, if I allocate one user high power, so other users may suffer from that power scarcity. In that case, that user fairness may not be maintained. So keeping all this in mind, we have to allocate the power among the users in such a way that user fairness should be maintained, interference remains within a tolerable limit, and the receivers, they are receiving the information, they can decode the information correctly. Second one, time slot. How to utilize the time slot? You heard about the TDMA technique. What happens there? In TDMA techniques, if there are, say, eight number of users, for an example, users, there are one frame is divided into 8 different slots. 8 different slots. So U1 will transmit first here, then U2, like U8. Then next, when the next frame comes, then again U1 will transmit. This is how the time is allocated. So multiple users can transmit through the same band, but at different instant of time. If we transmit in this using this TDMA technique, so obviously our data rate would be high and spectrum efficiency will be high. Second one, spatial resources, that is a kind of antenna and beams. Say if you want to if that receiver system is needs high data rate, in that case, instead of single antenna system, better use the multiple antenna system. Last class I already discussed diversity. Okay, now if you use a multiple antenna system, so obviously you can direct the beam to the particular user. If you have a directed beam, then data rate would be high. Another technique is code resources. Means you use, instead of time, instead of frequency, better you can use code for transmission also. That is used in CDN. What is happened? Each user is allocated different codes. They transmit to their intended users. The intended users is aware about this code. When they decode their information using their known code. Say for an example, say two user U1 is allocated C1, U trans T1, U2 T2 is allocated C2 code. When they transmit that, say it is transmitting X1 signal, it is transmitting X2 signal. The receiver UR1, there are UR2. Okay. When UR1, UR2, it is receiving both the signal. UR1 and UR1 is receiving both the signal. X1 and X2, both it is receiving. Okay. But when it receives C1, X1 and it is this C2, X2 is there. But UR1, what it will do? It will multiply C1, X1 with C1. So it becomes X1, C1 square. So it is X1, because if it is C1 square, it is 1. If it is C1 into C2, it becomes 0. So for what about the other signal? For other signal at UR1, that C2, X2 into C1, if I do, so X2 into 0, so it becomes 0. This is how it is decoded at the receiver. So code can be used. Now that I already mentioned the spectrum for a better understanding, that if you look at here, uh, some frequency bands, that is the LT bands are considered. Here you can see that is 5 megahertz band, 10 megahertz band, 20 megahertz band. Here utilized basically bandwidth is for data transmission 4.5 megahertz, whereas it is 0.5 megahertz for used for the guard band purpose. Similarly, for 10 megahertz, it is 9 megahertz for data transmission, 1 megahertz for guard band purpose. Just take an example that I already told. One resource block basically 180 kilohertz. That one resource block consists of 12 subcarrier, and each subcarrier bandwidth is 15 kilohertz. So 12 into 15, 180 kilohertz. So if I think about, say for an example, if I take the 10 megahertz band, 10 megahertz LTE band, all these bandwidths are LTE bandwidths, okay, LTE channel bandwidth, okay. There are 50 resource blocks. So 50 into 100, if we do, so it becomes 50, it is kilohertz into, so it will become 90 and kilohertz. That means 9 megahertz. So which is already mentioned here, 90 megahertz is for the transmission, and rest 1 megahertz is kept for guard band purpose. Now, why resource allocation is important? Spectral efficiency, energy efficiency, quality of service, interference management, maximize throughput, and user fairness. User fairness. See, for an example, if last class I discussed about a cognitive radio network where the user basically sends the channel, the secondary user sends the primary user channel if it is free. It opportunistically uses that primary user band for their transmission. That means there is a spectrum allocation. If we think about a cognitive radio point of view, there is a spectrum allocation because these primary bands are not they are underutilized since they are vacant. The secondary user band, which is already congested, they opportunistically uses that band. That is, it will increase the spectral efficiency. Now, what is energy efficiency? Energy efficiency is basically throughput by energy spent. What is throughput? Throughput is a successful transmission of bits, number of bits from transmitter to the receiver per unit time per hertz. That is the throughput of the system. So if I say throughput throughput divided by energy spent, that means per unit energy, how many bits successfully reach to the receiver from the transmitter is basically energy efficiency. Okay. So obviously, when I'm talking about throughput, so throughput, if you look at the throughput equation, that is equal to basically B, that Shannon's link, that Shannon's formula. Just a minute. Log to 1 plus SNR. When I'm talking about this SNR, that means transmit power for the signal channel square. Already I mentioned all this by, say, noise is here, some noise is there, and plus interference is also there. So automatically the power allocation comes, interference management comes, okay, channel is there. So if this SNR is good, throughput would be good, automatically quality of service would become best. And if it is, when I'm talking about fairness means at least if there are m number of users, all the m users must have some minimum requirement. When all of them satisfy that minimum rate, then I can say that user fairness is maintained. So that's what that allocation of resources is much more important. Now, what kind of allocations? It may be a static allocation, means it is a predefined, but it is this. If it is a predefined, it's not a intelligent one. But dynamic allocation is based, because it's based on the demand. Now, just take an example that I already mentioned previous slide, that throughput. Throughput. What are the, how we can optimize the or allocate the power and all to the users. See, the same example I've taken, that transmit, there's a transmit power, that is channel square, that channel gain, then interference plus noise. So I have, my main objective is to maximize the overall throughput of the system. RI indicates the data rate or throughput between ith user pair. Okay. When I'm maximizing, I have power constant, because say m number of users are there, so P1 plus P2 plus P3, P3 dot dot dot, that PM, that should be less than is equal to PT, that is a constant, power constant. There is a bandwidth constant, because you have to allocate bandwidth such you can, they must have achieved their minimum required data rate, and at the same time we have to maintain the QS constant, maybe in terms of SNR. Okay, so this is how we formulate a problem to address this allocation strategy. Now, what are the common approaches for this that resource allocation? One is sum rate maximization, one is max minimum fairness, or energy efficiency maximization, that I already mentioned in the previous slide, that is EE, that is this maximization of this, or maximization of this, or maximum minimum fairness, means minimum data rate maintained, and only maintaining this minimum data and how to maximize that achievable rate. That is the minimum max min fairness. Now, what are the techniques used when we are resolve these optimization approaches, or try to solve these optimization approaches? There is two type of problems. One is a convex optimizations, means that problem you formulate, that nature of the problem is either this or this. There is a minimum point or maximum point. That is called convex optimization. Another one, that non-convex optimization, when that your number of parameters are large. Okay, so in that case, our objective equation may not follow that convex equation characteristics. In that case, we have to follow some other techniques to get them to maximize or minimize our objective function. So for convex optimizations, we normally use Lagrangian water filling algorithm, game theory approaches. Whereas in case of non-convex optimization cases, use heuristic algorithm like genetic algorithm, PSO, okay, and machine learning approaches. Right now, all over the world, they are working on that. There is supervised, unsupervised learning, reinforcement learning, deep Q networks. So among all these, I will discuss one or two only, so that you can get some idea. So here, what are the parameters to be allocated? One is power allocation, rate maximization, WebDM resource allocation, team forming, energy efficiency optimization, network utility management. These are the basically different parameters that you can optimize. So that, what are the techniques? Already told you the techniques. For convex optimization, that is a Lagrangian methods. That means there is a Lagrange parameter. I'll take one problem on that. So it can, using this method, you can optimize the parameters. Similarly, KKT conditions are there, where it is that water filling algorithm is used for maximizing the sum rate. Gradient descent is another technique, okay, where you just reduce the error between the target and achieved parameters where that power control and beamforming optimized techniques are used. We can do, and sub-gradient methods are there. For example, say, just I'm taking an example, power allocation with total power constant. There are two users and total power is PT. So if I take that throughput equation, just keeping in mind that V is equal to 1, so I can formulate the problem maximization of, because two users are there, user 1 would be allocated P1 power and user 2 would be allocated P2 power. So obviously that maximization problem, it should be mod of square. There's a mistake. Okay. So that's subject to, this is basically our objective function, subject to P1 plus P2 less than 0 and P1, P2 should be always real number, that is greater than 0. So C is a coupled property. That means if P1 increases, P2 will decrease, or if P1 reduces, P2 will increase. So it's a coupled problem. How we can resolve this? So it can be resolved by Lagrangian dual decomposition technique. See here, what we are doing, we will taking the help of Lagrangian parameter. So if we look at that previous equation, that is log 1 plus mod of h1 square into p1 plus log 1 plus mod of h2 square into p2. Our constant are this. p1 plus p2 less than is equal to p2. What I'll do, I'll write the same thing, that is a L equals to same, just I'll add that Lagrange parameter into P2, because our constant was P1 plus P2 less than is equal to PT. So obviously I can write lambda is equal to PT minus P1 minus P2. Now I'll separate them. So lambda into P1 will come here, user 1 case, and lambda into P2 will come here. So I can reformulate the equation, this for user 1, this for user 2. So now maximize P1 to maximize this one. Better I say, you have to maximize this function for the optimal value of P1. That is your target. Similarly, that optimal value of P2. But at the same time, you have to keep in mind that P1 plus P2 should not exceed PT. This is how we can use the Lagrangian methods. If we do this, so for user 1, it will come like this. If you resolve this equation, I'll take a problem. There you can see that P1 can be, and P2 value is this one. This is at last when I likely to be a water filling solution. I'll tell you water filling algorithm later. Now this is the water filling algorithm. See how this water filling algorithm works. This basically this means Pi is equal to, say, if I say this is a parameter K, so it is K plus. If I say K, this means basically minimum of K and, sorry, it's not readable. So I'm writing in 1 second. Pi is equal to minimum of K and 0. That is the meaning of this equation. If I write K within bracket, that plus, the meaning of this one. So just later on we'll go to the discussion. See that 1 by lambda, that mu, it is mentioned here. 1 by lambda, this value, this level is this. This is the requirement, power requirement. Okay. This already the ith user already have. This much already ith user have. So this is indicated here. First user means sigma w square lambda square. So what is sigma 1 square? Sigma 1 square is mentioned here. If it is a h1 square, that means it is sigma 1 square. If it is a h2 square on a user 2 channel, then it would be sigma 2 square. So that is the power difference. The power difference basically from the lambda. So that much power user 1, the system has to allocate the 1. Similarly, that much power the system will allocate to the user. But in case of fourth user, already it has power greater than 1 by lambda, so it won't be allocated any power. So this is called water filling algorithm. I've just taken a little bit theory on that to how the power is allocated among the users, and I'll take a small example to give you better picture. So just say for XI, so I for ith user, XI is the transmitted information, channel is HI. So the receiving information would be XI HI plus that EWJ noise, where PI is the power, that is expectation of mod I XI square. Okay, and so ith user SNR is this one. Already I mentioned number of time. So what is the ith user capacity or rate? That is log to 1 plus SNR. So now my target, I have to allocate power keeping this condition in mind. So that my problem formulation, that is a capacity that I have to maximize for T number of users are there. That's what summation is equal to I is equal to 1 to T. I have to maximize this capacity, keeping the constant, that is sum of Pi less than P. So when I write using Lagrangian problem, so I'll write the equation first, this part first I'll write, which is written here, then lambda, that Lagrangian parameter, into P minus Pi, sum of Pi, this part. This one is here, the constant. Then I have to differentiate with respect to, since I'm allocating power, we have to, so I have to differentiate that function with respect to Pi. If I differentiate, I'll get this expression. This expression I'll get. Now, if I reduce or expression, it would come like Pi is equal to this equation would automatically come, because that from differentiation, you know, the already minimum maximum how we have to do. First you have to take the differentiation, then you have to equate it to 0. Then if you resolve this equation, so that's what it is equated to the 0. And if you resolve, automatically this Pi is equal to 1 by lambda minus sigma w square by mod of h square to the. So that we can write Pi is equal to 1 by lambda sigma square w square mod of h square. That's plus sign already discussed. That means it is mentioned here. If it is x plus means max of x and z. Now here see, if 1 by lambda is greater than this basically this much power that ith user required, and the ith user has this much power. If the requirement is high what the user has, then okay, fine, that means this condition, then this much amount of power it will be allocated to the ith user. If it is this condition is wrong, if it is the user has higher power from the requirement, then it won't be allocated any power which is satisfied with this condition. Already I discussed this water filling algorithm. Now I'll take a problem. Say, consider a 3x3 MIMO channel. 3x3 MIMO channel have same variance with of each channel noise is equal to 1. Gain of the channels are given this one. So if you look at the channel matrix, it would like 52, 13, and it would be 2, then 0, 0, 0, 0, 0, 0. Okay. Now see here, if the total power is 2, you have to allocate among these 3 users. U1, this is for U1, this is for U2, and this is for U3. Total power U is U2. I have to allocate the power among U1, U2, U3. How we can? So I've taken this that formulations. This one, the total power already mentioned. That is already mentioned. This Pi is equal to 1 by lambda sigma w. This is the power allocation. So if I have 3, there are 3 user, Pi is equal to what I can write, I is equal to 1 to 3. Then that power should be less than is equal to PT, that I already mentioned. Power constant should be maintained. Keeping in mind, I can formulate the expression. This equation total power is P. It can be formulated. So I can write that 1 by lambda 1 to 3, so is equal to P. P is given to. Now, if I put I is equal to 1, I will get 1 by lambda sigma W square H1 square. Similarly, for second user, for the second user, this is for second user U2, this is for U1, and this is for U3, user 3. Is equal to 2. From there, I can value what would be the 1 by lambda. That is the maximum level. Keeping in mind, I can see now P1 is equal to 1 by, what was the formula? If you see 1 by lambda minus sigma W square by mod of H1 square, HI square. So sigma W square already it is mentioned. Noise is basically that sigma W square is already mentioned. Sigma W square equals to 1 is already mentioned. So for each equation, so I can write here, for this equation, I can write, what I can write, 1 by lambda minus, since that it is 1 by H1 square. That means that H1 square is basically 52. That's what is it, 1 by lambda 1 minus 52. It will be approximately 0.76792. P2 would be, similarly, you can calculate 0.77 and P3 would be 0.5321. So this is how the total power can be allowable total power, means available total power can be allocated to 3 different users to maximize the sum rate of the system. Now, this is how that Lagrangian and all are used. Now, another that already that convex optimization I told another one is a game theory. In game theory, what happens? In game theory, say if I take the same problem, but here each user try to maximize this own data rate. There is no central control. If we look at here, there is a central control. The power is allocation, but here it is no. So that's what, since each user is wants to maximize its own data rate. So I can forward the expression, that equation UI is equal to log 2 1 plus HI square this, and P1 plus P2 is less than is equal to PT. So that's what, since each user is trying to maximize his own data rate. So in game theory, there is that he has one pricing parameter called lambda. So that same problem can be formulated as log 1 plus this one into lambda minus lambda into pi. Okay. Then then same way that the derivation you have to do. So almost same type of water filling kind of things that formulation will come. Here, when we resolve this, that P asterisk that is called Nash equilibrium. That P asterisk, P1 asterisk plus P2 asterisk should be equals to P2. That's Nash equilibrium should follow. We have to choose the lambda in such a way that it should maintain the Nash equilibrium. That is the concept of that game theory. To maximize the user that is each user's that it may be a data rate or energy efficiency, whatever. So what are the important insight in game theory? That is, users are act selfishly. Price lambda controls the total power usage. When price increases, user reduce power. When price decreases, user increase power. Equilibrium automatically satisfies the power content. These are the basically takeaway from this game theory. Now come to so these are all discussed. I discussed about what are the resources, how you can allocate, what are the possible techniques we can use for maximizing the resource allocations, for resource allocation to maximize our objective. That objective may be network throughput, maybe reducing system network outage, maybe to get better energy efficiency. So depends on objective, we can choose our optimization techniques. Now, come to the that cellular network architecture. In cellular network is basically that in cellular network that right now, if we think about our handheld devices, say mobile phones, we are all connected with base stations. Uh, so we are using basically that cellular technology, you can say. In cellular network, what happens now that entire geography, say for an example, total says this much area is there. Uh, they are divided into different number of say cells. Normally, in theory, we used to consider hexagonal cell shape. In practice, it is irregular. Now we may raise to one question: why hexagonal? The reason is basically this is first of all, it can cover if you it can you can consider a circle. Okay, fine. If I do the circle shape, then say even if the three different boundary touches, then we'll cover this region. We'll cover this region. So different geometry has different problems. But if you look at this hexagon, this first of all it covers the much more area, as well as whatever the problems that we may face if we use other geometry, it can be overcome by this hexagonal geometry. Okay, so each I'll say of certain area is divided into different number of cells, and each cells is served by a base station. Base station, base station. So there is a user, so it has another base station. So this is called cellular technology, and it operates certain bands. Say for an example, if I think about a GSM network, GSM standard, in that time 900 megahertz, basically 900 megahertz was operating frequency. So maybe say total 10 or some band is allocated to among these cells, and these cells basically, and the users are supported by this that allocated bands. Just more clearly, if I say better I say each cell, say say uh, better I say a cluster, a cluster cluster consists of n cells. Means like this, say here it is a 1 2 3 4 5 6 7 cell cluster. Here it is a 7 cell cluster. Okay, it that 7, that is a typical value. It may be 4, it may be 12. It's not any integer you can't take. That 8 depends on that I, some formula is there, I square plus j square into I plus j. It has some geometrical from so geometry it will come. I'm not going to the discussion. If I put say I is equal to 2, j is equal to 2, that value becomes 12. If I put I is equal to 1, j is equal to 2, then it becomes 7. So it has some specific values it can take. So say a particular number of cells make a cluster. Total available bandwidth for the system is allocated among these cells. Say if we have total bandwidth B, so B is divided among all these 7 cells. And this allocation, the same band would be allocated to the other cluster. That is the concept. That is called frequency reuse. But when this allocation is done, say if it has a say some band say X, it should be allocated Y. That the difference between of X and Y band should be large. Otherwise, they may create interference to each other. Anyway, we are moving towards the different directions. Uh, my main concern here, in case of cellular network, the users are supported by the base stations. Okay, so if the number of users increases, then base stations may suffer from traffic burden. Now, how it can be handled? So every day, if you look at that, the population is increasing. Every day the number of users are increasing. So obviously, every day there is a traffic burden to the traffic burden to the base station is increasing. So how it can be handled? That solution is device to device communication. What happens in device to device communication? According to the device to device communication, if the user are nearby, instead of sending their information through base station, they can send themselves directly. Normally, what it happens, say two users, they can see each other. They say even they are sitting within a single room. User A and user B, they are user A and user B, they are sitting inside a room. If A wants to call, say send some information to B, now according to the cellular technology, it has to go first the base station, then it moves back to the B. But D2D communication tells no need of base station since they are nearby and they can see each other, they can send them directly. So if they send directly, obviously you can see, so there is a traffic upload to the base stations. So base station would be free from this traffic. So this is how that D2D communication concept came. So what is D2D communication? Allow nearby devices to communicate directly with each other instead of routing data through the base station. How D2D helps the cellular network upload traffic from base station, reduce transmission delay. Obviously, if A directly sent to the B, so it will take less time. Now, initially, if you think that A first, that information of A first reaches to the base station, then it moves back to the B, so it will take time. So it reduces the delay, and it will also improves the spectral efficiency. It increases the saves the transmit power, because if the base station comes, so there's a power, obviously power expense will increase. So since base station is not in right now, not in scenario in case of D2D communication, so the power consumption will be less. So enhance silage performance also. So if we use the D2D communication, we can increase the coverage area. I'll show you. So the research that emerging research directions, energy efficient D2D, research assisted D2D, UV assisted D2D, AI driven autonomous resource control, and NOMA D2D. These are the current research trends. Yeah. D2D communication is defined as already mentioned, that direct communication between two users in close proximity, that already mentioned. It uses the cellular resources and improves the spectrum efficiency at a cost of lower transmission power. Fine. I already mentioned in D2D communication, use may use the cellular base stations or may not. Okay, if we look at how it can operate, D2D in D2D communication, two devices, they can be operated in in-band. In-band means basically they works in the license band. Means they are using the cellular network resource. Resource means spectra. They may operate in out of band. They may use unlicensed band. In that case, they may use Wi-Fi band or Bluetooth band. If they operates in band, that means when they are using cellular users, then they may use it underlay and overlay. Now the question comes: what is underlay? What is overlay? Underlay overlay means, if you look at here, for an example, say if you want to access my room, for an example. So obviously, if I am present in the room, if you want to talk to your parents or your friends over phone, you have to speak within a control limit, because you are sharing this my room, and I'm present in the room. So that means you are sharing since you are sharing, you cannot shout. You have to talk your parents or your friends with a controlled manner. Similarly, since in underlay, D2D uses the SIU spectrum while the SIU user is present in this channel, means SIU user already transmitting through the channel. Under this condition, D2D wants to access that channel. In that case, when it uses the channel, that cellular channel which is already underused, it cannot transmit with a high power. It has to transmit the control power. And the sharing scheme is called underlay transmission. This sharing scheme is called underlay transmission. What is overlay transmission? When the cellular user is present, that time D2D won't transmit. Means, what is the analogy? If I am not in room, you are accessing the room, but when I'm coming into the room, then you are leaving my room. Similarly, when the cellular user is present in the channel, means they are transmitting, cellular user are transmitting because their bandwidth is, the D2D users won't transmit. But if you look at this time and this time, the cellular is not transmitting. During that time, the D2D users will transmit. That is called overlay transmission. Now, what are the strategies that they can directly transmit? They can transmit through a relay. Through a relay means D2D transmit its own information to the relay. That some access techniques are there. Decode forward means it will accept the signal, then decode the information, eliminate the noise, it will boost up the signal, it will transmit to the DR, means D2D receiver. Another one is an amplified forward method. That is, it will accept the signal, amplify and forward it. So there are a lot of relaying protocols are there. I'm not going there. So that is with a relay-based D2D transmission. Another one is multi-relay. See, these D2D users wants to transmit this data. Multi-hop transmit it is called. It will the signal will be received by this R1 and a first relay. There will be a second relay. N number of relays are there. Then it will forward to the receiver. So if I use this strategy, I can extend my coverage area. Now, case study 1, where cognitive radio-enabled D2D communication using hybrid transmission. Already I discussed that cognitive radio network. See here, our network is considered. These are the basically D2D transmitter. In number of D2D transmitters are there. These are the D2D transmitter. In number of transmitters are there. Similarly, in number of receivers are there. Okay. First, the transmitters will sense. This is basically CU user. Okay, CU user, it will first check whatever the signals available in the CU channel they will receive. They will take their local decision based on, say, whatever the signal it is receiving. It will check based on some set threshold whether that CU signal is present or not. Accordingly, say it will take some decision, 1 or 0. If it finds that user is present, the CU user is present, it will take 1. Otherwise, it will take 0. So that decision, these decisions are called hard decisions. These decisions will send to the fusion center. Then, using some fusion rule, it may be and or majority, different rules are there. Based on that, overall decision made, and that overall decision is conveyed to these transmitters. If the decision goes in favor of that, the C user is not transmitting, means user is not present, then they may transmit. There is an overlay transmission to transmission. Another, they may find the user is there. That means the decision goes in favor of presence of CU in the channel. In that case, if they want to transmit, they have to transmit the shared transmission. That is an underlay transmission. This is our scenario. See here. So that equation is formed. That this is H0 hypothesis. Already I discussed in the previous lecture. H0 represents only noise is received, means user is not there. It is CU user basically, and H1 indicates user is there. CU means cellular user is there, where This is the cellular user signal, cellular user channel, and AWG noise. This is the frame. First, the sensing time based on the sensing decision that this users will transmit D1, D2, that to DN will transmit either underlay or overlay transmission based on the decision. If the decision goes in favor of presence of CU, then this D2D transmitter will transmit it underlay, else they transmit in overlay transmission. So this is the total throughput formulations. This is the number of details is taken from some paper our work. Just the equations are there only. So overlay throughput, underlay throughput. Okay. So if you look at, and this is the outage expression. This is the total outage expression. So if you look at the outage characteristic, you can see if the sensing time increases, the outage decreases, reaches to a minima. Then if the increasing time increases further, then again the outages increases. That means if I think about this green curve, this is the optimal sensing time. So the sensing time. So the system will allocate. If I talking about the green line means one user is there, total frame time 100 millisecond. That considering this condition, the system will optimize that resource. It is a resource allocation. The sensing time would be some approximately around 3 or 2.8 millisecond. If it follows, then it will achieve the mean. It would the system performance would be best because in that time during for this allocation the outage is minimum. If outage is minimum, that means the receiver is receiving or decoding most of the data, most of the information successfully. If you look at the second figure, that with the SNR increases, then if we find that outage is decreasing, which is normal. Here, another thing that wave fading channel is used. Waving folding. This is also another folding channel where the fading parameter is VUV. If fading value of the fading parameter increases, that means channel condition becomes good. So which is reflecting here, since the V is increasing, see from black, then blue, then that pink line, that for V is equal to 3, that outage is minimum for given SNR. Okay, clear? So outage we come to know. Okay, fine. Next, second case study, that is nonlinear energy harvesting CR-enabled sensoring based D2D communication. Here, another interesting feature we considered, if you look at here, the same concept. Here, the first of all, energy harvesting we incorporated, sensing time. Thereafter, two different blocks we considered. One is sensoring and energy harvesting. The green communication, next class I will tell about. That's what this I've taken. Energy harvesting is a part of green communication. What happens? For the sensing is the sensing already discussed. After sensing, say whether it is underlay or overlay transmission, the D2D users will transmit to their peer. Now it may happen. So these are the sensing and reporting channels. These are the sensing and reporting. Black dotted are reporting channels, and red dotted are sensing channels. But these are the transmission links. The problem is it may happen, see, n number of users are there. It may happen that one or more users may suffer from blockage. Here it is nth user. Means channel is heavily faded. If this happens, then in that case, that information may not be delivered to the user successfully. Or even if it is delivered, it will be distorted much. The receiver user may not be able to decode the information successfully. Now, the problem is how I can maximize the system throughput. How I can maximize the system throughput. One way, see, if you allow all n transmitters to transmission, say i- if they follow TDMA technique, so total transmission time will be divided among all n users. So this times may, if I follow the TDM transmission technique, say D1 will transmit, this time may D2 will transmit, and this time DN will transmit. Since the DN block is DN, that link is heavily faded, and uh, that information cannot be delivered, or if delivered information that would be much distorted, so it cannot be recovered. So basically, that transmission is not useful. That means this time, a portion of this time not basically utilized properly. So what would be the solution? One solution we can do is we can eliminate this nth user from the transmission process and divide the total available time among the n minus one of n minus users. So this is the how we are allocating the resource. That here my resource is time. I'm utilizing the time more efficient way. Instead of allocating to everyone, I'll first look at who are in good. Now, how you can take care, how you can capture this effect. So, how you can eliminate, allocate these resources to the those who can successfully send the informations. So that's what one censoring technique is adopted. What is the censoring technique? The censoring technique is that normally before transmission, the channel that estimation is done at the receiver, and this estimation is feedback to the transmitter back. Normally, normal transmission process. If that estimated channel is greater than some threshold, they are allowed for transmission. If not, if it is less than CTH, it would be eliminated from the transmission process. This technique is called censoring of the user. So if we adopt these censoring techniques, it may happen one or more number of users. Those channel condition is very bad. They can be eliminated from the system, and the total available transmission time can be allocated to the rest users, those who have a good channel condition. This is how we can improve our system performance. So this is energy harvesting. Next class I will talk. Right now I will not talk. So see the same thing, it is shown here. Initially the conventional that is in if you see the total transmission time, if you look at this here, initially if you look at here, initially the total available time is divided among n minus L into T. The time is divided among n into T. Now, since L users are eliminated from the process, so now n minus L into TR time, total time is divided among n minus L, because L number of users has bad channel quality. So L number of users allocated, eliminated, n minus L into T number of that n minus L into TR. The total time is allocated between n minus L into T users. Okay, right. Better I say this way. Better for this case, okay, total transmission time is divided among n user. For this case, total transmission time is divided among n minus L user. This L number of users has bad channels. So that's what we found, that not only that throughput increases, that spectrum utilization is also improved. So this is the throughput. You can see sensing time increases. See, interesting. Sensing time increases, the throughput of the system increases, reaches to the maxima, then again start degrading. That means for this condition, what are the conditions considered for these simulations? This is the optimal sensing time. It may approximately around 4 something, 4 point some milliseconds to achieve the high throughput. Okay. Another one you can notice here. See, if we increase the censoring threshold, the throughput of the system also degrades. Anyway, maybe some reasons. What the reasons? In the conventional CTH increases, channels eliminated, resulting in low throughput. It is observed in the proposed schemes CTH, obviously, and CTH throughput remains. Okay. Got it. This is the conventional system. In conventional system, if the censoring that some algorithm is initially it was noticed that if the censoring is incorporated, the throughput is degrading. Then some algorithms was proposed uh, through by which we what we have received that see this is the proposed analytical approach means through equation, and these black lines are simulations. Even if we increase from 7.5 to 1.5, the throughput remains same. There is no degradation of throughput. Okay. And if you look at here, improve of strict purpose from different, if we increase the number of users, okay, so that improvement in speculum utilization also increases for a given censoring threshold. Okay, this is another throughput, same optimal, different channel it is tested, different channel Weibull, Nakagami, Raleigh. Okay, fine. Some applications area: disaster management, public safety, social and commercial services, vehicular network, cooperative communities. These are the applications. So this D2D communications helps to extend the network coverage in non-functional areas. It can communicate through licensed band or through unlicensed band. In licensed band, transmissions can be underlay as well as in overlay. D2D communication improves the spectrum efficiency. It consumes less power, thus it's suitable for energy constrained network as per it. Okay, performance can be investigated in terms of throughput. Okay, fine. So these are the references. Thank you. Any questions? Already I discussed about.
Any questions?
Okay, if you have any questions, you can put in the chat box. I will address it. Okay, sir, shall I stop?
Yes, yes. Thank you very much for talk. Then we have next talk is on.
I think we will look at next week. This week there is no talk.
Mhm.
Okay.
Okay. So yes.